Okay, so let's begin then the session.
Yeah,
Yeah, I'm hoping for more people to join in, but maybe it will be good at this point to even do a quick introduction to what Nudes in the Classroom as an initiative is, and of course, introduce Nic Bao, who is joining us here from RMIT, Australia, and and we are extremely delighted to have him here. Um, a lot has been kind of promoted and said on our social media platform, but we are hoping for a very, very interesting and an intense session of discussion afterwards with Nick. So let me begin this session by just quickly introducing Nudes. Nudes operates within the realm of cross-disciplinary culture of art, architecture, and computational design, powered by digital making tools addressing larger network of social, cultural, and environmental exchange. For many of those who are joining us from Mumbai and India and across India, you might be familiar with the principal architect Nuru Karim's work for Nudes. During pandemic in 2020, Nudes also opened up a sub branch of offering teaching platforms as well, and offering opportunity for many of the young architects and practitioners to operate within this subgroup called Nudes in the Classroom, which aims to create a learning platform of and community of like-minded people to expand this research. This is an initiative to support students to grow beyond financial hardships and learn from leading experts in the industry. This initiative also offers a lot of support to students in terms of getting a certain scholarship to attend our workshops, a lot of our lectures such as this, where we invite experts from across the globe to join the session for free. All our public lectures and conferences are free to join us on Zoom. And one such session begins today with Nic Bao. Nic Bao is a registered architect, director of BDW Architects, and founder of Form X. He is also a lecturer at School of Architecture and Urban Design, RMIT University. Nick's research explores design methodologies for establishing a complementary relationship among computational design, structural engineering, behavior algorithms, robotic fabrication, and additive manufacturing. It's a very impressive and an extensive work that Nick has been doing. Nick is completing his PhD at RMIT, where he gains the Bachelor of Architecture, and he completed also his Masters of Architecture at the University of Melbourne. His works have been exhibited and published extensively, recognized as at national and international levels. Nick also received 2022 Grand Prix Design Paris Award and Gold Award, which is a Gold Award, and 2021 Muse Design Award. Nick, congratulations on your recent award at Grand Prix. And welcome to Nudes in the Classroom. The platform is all yours.
yeah. Thank you for invitation and introduction. Yeah. So I'm going to share my screen. So yeah, can you see my screen?
Yes, we can see your screen.
So it's in the presentation mode.
Yes, in the presentation mode.
Okay. So hello everyone. Yeah, welcome to my lecture. So the topic is my lecture's topic is about performance driving architecture design and structure optimization as a form finding tool. Although I will introduce the form finding digital way, but I will also introduce the couple of projects which are using the robotic fabrication as a construction method in my projects. So briefly, yeah, I have been introduced already. yeah, just want to quick have a look for you. I'm a lecturer, also as an assistant professor at MIT in Australia, and I'm the coordinator of the architecture technology course, and I'm also registered architect in Australia, US, and the UK. Um, and I'm the researcher and key member in Center for Innovative Structure and Material, which is directed by Professor Mike Shear's team, and also in the Tectonic Information Lab, which is directed by Roland Snooks. Yeah, like Bevan talking about before, if you are interested in apply MIT PhD, you can also contact me. And yeah, I'm also the founder and director of my own practice, BDW Architects, and the FormX Tech, which is for the 3D printing large-scale architecture. Yeah, I'm also the community member of several associations, including Cadular and Digital Future. So it's quite lucky Cadular conference will host in India next year in CEPT University. I think you are more familiar than me. So we might meet in person next year. Okay, this is a quick look of my recent or in project or in the past few years. So the topic I'm going to talk is the performance driving architecture design and structure optimization. So the background is and the motivation and problem of my research come from the three aspects, which is inspiration by the nature and the collaboration between architects and engineers, and also the lost connection between complexity and efficiency simultaneously. So another one is the imbalance between architecture aesthetics and the structural performance. So my research is for the algorithm for intricate forms and also the mass customization manufacturing of the construction industry. So to achieve this research aim, so a few questions will be addressed. One is a collaboration, one is the aesthetics and the performance, one is the advantages for the topology optimization methods, and also robotic fabrication. So start from some precedents, like the left image, the Gothic building and the Gaudi's church from very early ages. And now for the smart slab from DFAB, ETH, and the fiber pavilion from ICD and ITKE. So you can find some you can find all the forms inspired by the nature. So especially it's from the nature structures. So how can we balance the aesthetics and the performance, and which is the architecture vs the structure. So form from nature, then how can we generate the nature form rationally? So start from this apple. It is the simulation of an apple shape optimization by Professor Mike Shear. Then later, Professor Mike Shear proposed a BSO algorithm, which is the bidirectional evolutionary structure optimization method. So we also improve this method and do some adjustments and attend this national computation on the aerospace structure optimization, and we got the first prize. So you can see the material is being removed step by step. Also, it's still keeping the similar structure performance. So this method has been tested on several architecture projects. And more architects and designers start to using the similar method to do the architecture design. So this is Amoeba software, which is based on the topology optimization software algorithm based on the BSO techniques developed by Professor Mike Shear and his team. And I'm also the part of the team, so you can also try this one if you are interested in. So yeah, back to the topology optimization, generative design. Later, we also are using the robotic fabrication to apply on the architecture application. Mainly, we use the MIT Architecture Robotic Lab, which is directed by Roland Stux, to realize our design using the large-scale 3D printing technology. So the main material we always use is the clay concrete, polymer, and one metal print. So I start from the first project. First project is called XForm 1.0, which is digital future, which we're doing the digital future in 2019. So you can see the left image is the tree. The middle image is the Gaudi's church. Then we design and optimize a column, which is very similar with similar appearance with this the tree branches. So after we mirror it and also making it into a pavilion, and the top view it looks like Gaudi's church ceiling, and the column looks like the tree-like branch column. So this is the optimization progress from a very fat model. Then we do the optimization, then do the smoothing. Then later on, I use the small 3D printer to print each part. It's 1:10 scale, and testing to check if it can be assembled and also can be built. Then the left side is a small printer, small 3D printer, which is I believe most of you already used it before. And the right side is the large 3D printer we developed at MIT University, and can print 2-meter high models, but because limited by the seating, so the maximum print we can achieve is 1.7. So this video showing the printing progress. We use the KUKA 150 to print the column for the pavilion. And yeah, the whole lab is directed by the Roland Snooks research lab. Now it's called Technology Information Lab. And the right side is the grasshopper simulation. So after that, I'm going to polish the surface and to remove all the streams, the plastic streams. So we bring this big 4 columns from Australia to China. And we also design the joints on the top and the joints underneath. So the joints on the top can be used to tie the plastic tie to hold the laser cut top, and the lower part we're using the steel plate to fixing on the timber grounds. So after we deliver to China, and students from Digital Future help us to assemble. So because we want the students to involve in the assembling progress. So you can see that another model next to us is Jules Resin's model, which is from UCL. So this is a final work. So the project is leading by me and Xin Yan and Mike Xie, and it's about 2.2 meter high, and we divide it into we divide this into two parts. Then we design a joint in the middle. So the next project we improve this the algorithm, and also to making the more branches. The difference, you can see the original design domain. The previous one is the flat top with only 1 column. Now we're making 3 columns, and also the 3 curvy top. Then we divide it into 4 pieces because this is a symmetrical form. Then we only optimize on a quarter of the model. Then we're adding the boundary conditions underneath, and also adding the normal pressure load on the curvy roof surface. Then we run the algorithm, and yeah, 52% of the material slowly being removed. So compare with the nature growthing branch, and you can see our optimized structure is also achieving the tree-like branch. Then the right size is a quarter of the model of the overall simulated form. So the the quarter of the model is a 4 meter by 2.1 and by 1.85. So the full model is 4 meter by 4.2 and 3 meter. So after we're testing this new structure of the pavilion, it still meets the actual structure requirements, has very less displacement. Compare with X-Form 1.1, X-Form 1.1 and X-Form 2.0, you can find the big difference. So also compare with the full model, 2.0 pavilion has more complex geometry inside and has more branches. This is the single column comparison. The same progress, I used the small 3D printer to print a 1:10 scale model, which looks quite successful and can be printable. So the big challenge is we're gonna make in 1:1 model. So for the 1:1 model, we attended ISS conference in Barcelona 3 years ago. So we have to carry it by ourselves. So that's why we divide it into 25 pieces. So we use the robotic to print 25 pieces and bring to the Barcelona to attend the conference. Then the overall assemble time is about 5 hours, only 2 person, but the overall printing takes 200 hours in Melbourne. So you can see this is final 1:1, a quarter of the model, because we cannot bring the full model, so it's a bit pity. So this is assemble progress. It's very efficient structures. Also, this project also win the International 3D Printing and Design Competition in 2020. Later on, I want to introduce a collaboration project with Roland Snooks. This is called Cloud Effect. We are using the algorithm to develop the form, which is using the Roland Snooks code. But my main contribution is to making the algorithm, making the form have the real-time structure feedback developed in the Grasshopper. So this is the algorithm and the line joins from Roland's project. But what I make it to have the real-time structure performance. So you can see this is the first edited version of the structures, which has the red color means the large deformation. So I'm helping with to detect the most weak point, to improve it, then to real-time fixing the deformation error. So you can see the to edit the carbon fiber into the different branches, so it's have less deformation. So later we using the still using the 3D printer to print the form. So this is can put into the can make it carbon fiber infuse the 3D printer tectonics. So you can see there's 3 layers. Outside is the 3D printing PETG skin. The black one is the resin, infused resin. And the gray one is the infused carbon fiber streams. So this is a final model. Then we also write a paper called Super Composites. The co-author is Hassan Mohammed, myself, and Roland. So this is the video showing how this project looks like. This is a digital model. So you can see external, the plastic transparent skin. Internal is the carbon fiber structures. Yeah, the render looks much better than the real project because in the real life, the printing can have little bit different difference on the real material. But it's not too bad. So we build it and also assemble and deliver to China, exhibit in the Shenzhen Biennale. It's a large team project led by Roland and fabricated by us and structured by myself. So this has happened 3 years ago. And last year we improved another one. So we called it Sample the Future. And we exhibit in the National Gallery of Victoria in Australia. So we're making another version, which is improved a lot of, improved a lot. And I'm going to show you, and also I'm improving the code to make it more efficient and more faster on the simulation. So this is the testing for the real-time structure feedback. And this is the final project. Now, this time we're making it into 2 pieces. One is on the ground. It's like Iceland sculpture on the ground. Another one is the 2 wings hanging on the wall. So this is a final image we exhibit in the gallery. So one piece is on the ground, another piece is on the wall. So my main contribution is still the structure and also fabrication and robotic 3D printing. Yeah, so this is the final project exhibit in Australia. Later, this project called the cast bodies, which is part of my research. Using the similar algorithm, similar method to design the combination of the structures, which is the testing structures, and to feel the making this model is the sacrificial concrete mold. Then we cast the concrete inside. Then the project has been selected as the Venus Biennale. So this is a video, which you can see the concrete casting into the model. And yeah, so this is the beneficial for the robotic fabrication can print the intricate form and for the complex architecture geometries. And the sacrificial formwork also is like an ornament for the project, making the concrete much nicer. So this is a real project. Last one is only the digital video. And we're making 2 models, which another one is not sacrificial formwork. We can also to remove the form, which is only have the concrete left. But this is only have about 700 millimeter high. It's also only the test. But for the last year, Roland and myself, we also developed another project which called tectonic formation. It is using a similar way to design, which is aging bodies. Then we 3D print the mold, then cast concrete. Then after that, we design all the joints and remove after we're removing the demolding, remove the mold, which is demolding progress, then they have this aging body, casted aging bodies. which can easily to remove the mold. So we plan to develop this kind of agent body using the algorithm to develop a wall like this. And also we instruct our students. So this is a student work from my design studio, can develop this patterns into the architectural facade, also interior wall as well. And from last year, Roland and myself, we start to develop some the new technology for to develop to helping with this kind of geometry. So we start to using the robotic wire printing to achieve the similar geometry for the architecture. So this is only rendered, which is pretty good quality. Because of the lockdown, the project started, this research started from 2020 because of the COVID lockdown. So we collaborate with the University of Wollongong to helping me to print this one project, which called cast bodies. So you can see the quality is not achieving quite good because it's only few early testing. It's the one project also same geometry, but testing using the different material and 3D printing tech. This is a final geometry. It's pretty good, but it's not perfect. So from this year, I'm also developing the with Roland using the MIT facility to develop a new one technology, which is attending the Melbourne Design Week this year. If some of you see our Instagram or Facebook, you will see this project. So this project designed by Roland Snooks and also collaborate with my company, FormX. We print and fabricate as a sculpture. So this is the final printed project we exhibit in the Melbourne Design Week and the Melbourne Design File. Then later, I'm going to move this project to my friend's winery as a permanent installation. So we're using the one to print the geometries, which using the algorithm developed. So you can see the quality is much better than before and very high resolution. And this is the photo from exhibition. Also want to introduce the next project, which called Intelligent Form. So this Intelligent Form is supported by Digital Future and also China Construction. It's using the topology optimization to achieve. We set up a two wall, then using the topology optimization to generate the patterns. And we're fixing the bottom part, the three bottom part, and the loading and the wing loads to get the material removed. So this is topology optimization method. Then later on, based on the geometry, I'm doing the model and to try to make it nicer and smoother. So this is same method, 1 to 10 printed small model. Testing the performance, very similar, less deformation, looking quite good. And later we have to make it 1-to-1 model. And we use 3D printing. So we need to design the mold. So you can see we design the mold, design the joint, design the fringes, which can connect with each other. And this is the side part, this is the middle part. Then we send the mold to the factory in China and fabricate the mold in China piece by piece. So this is the large piece on the side. This is the middle piece in the middle. So then we're using the new technique, spray the UHPC concrete. So you can see the workers, they're working on it to spray the concrete on the mold. So this is the first layer of the concrete. And to make sure they were not leaking in the in each gap. So this is final layer. So the overall is very thin concrete. Then after demolding, then we're also polishing the concrete on the surface. And this is the middle part. Yeah, so you can see middle part, we demolding this piece of the mold. And yeah, this last piece, which is to protect the edge of the concrete. It's very heavy. Then we deliver it into Tongji University in Shanghai. And we're making some holes on site. And there's major three big parts, 1, 2, and 3. Each piece is about 150 kilogram. So we need a lot of people on site to help us. Some of them are students, some of them are workers. So it's very large pieces, and we assemble it on site. Yeah, so this is the final piece. So this is the video from site. So you can find we still have the steel one to hold it because we finished the project very late. The concrete, the best performance of the concrete is after 28 days. So after 28 days, we remove this this one. Yeah, so it's a digital feature. I think it's also there's a Indian, also, a lot of Indian students also attending the digital feature. Hopefully this year will also happen. Yeah, some photos on site. So also my teaching related to a lot of my research. This is my design studios. The top one is all my design studios, and the lower one is the workshops. So just quick look.
Design studio Forming Complexity was founded by Nic Bao and Hassan Mohammed in 2009. The studio has been running for 2 years at RMIT University Architecture School. Nic and Hassan are both registered architects in Australia and PhD researchers in architectural engineering technology. Forming Complexity is a design studio in the territory among digital fabrication, algorithm design, materiality, additive manufacturing, and the structural optimization of complex forms. This studio aims to explore advanced architectural design and tectonic implications of carbon high-tech composite systems, accompanied by new fabrication techniques such as 3D printing and robotic fabrication in the architectural context. Now, robotic fabrication and 3D printing are rapidly changing the feasibility of constructing geometric structure with a high degree of intricacy. Therefore, emerging architectural design approaches that leverage the capacity of algorithmic design and digital fabrication methods, such as robotic fabrication and 3D printing, are able to create a highly intricate built architecture in the near future, especially in the city of China. Through a series of generative design form finding, a number of designs will be proposed to achieve exceptional architectural qualities such as complex formal expressions, interesting spatial qualities, and innovative digital fabrication methods. The studio will explore a series of architectural components and building systems to reimagine architectural style influenced by the implication of robotic fabrication and high-tech composite materials in other industries such as aerospace and automotive, which have transformed the culture and approach towards design and fabrication in these industries for many years. students will design a series of architectural components and building systems to reimagine architectural style. The new design proposals for the future city will accommodate fabrication constraints as well as aesthetical qualities and planning consideration through developing and testing new intelligent design methods and new construction techniques.
Yeah, so in my design studio, there's so in my design studio, there's I sent to using the same similar methods also to produce using the combined with Swan and topology optimization, then later testing the fabrication. So yeah, the images from my design studio work, student testing the different geometry and also fabricate to make it the intricate form have the structural performance. This is a few project from Digital Future 2019. The student designed a Chinese heritage building using the topology optimization. This one is last year, the buyout form. And there's one very excellent project, Digital Future 2020. They're making a new Eiffel Tower using the topology optimization methods. After that, we help them to print it. Then this one is the Scheduler 2020 in Thailand. Then we run a workshop to ask students to redesign the last secondary familiar, changing the facade. And this student, I remember she's from AA, and she used a similar method to design a staircase. Okay. Then the last year, we're working with the China construction team, and one is doing the big fabrication, and another one is design the projects. So I think, yeah, there's one student in the audience also attends doing the project. Yeah, so the student using a similar method to design a bridge. The student designed a sand gallery. The student designed the weir, which is the large, which you can find in some theme park. Then it's very nice render. So we help them to do the 3D printer. So using the 3D printing to print the geometry. And this student designed another Chinese heritage, but in each architectural components and assemble on site. So yeah, they assemble into a big, large architecture, which is to helping to rebuild the Chinese heritage. And this group of students, design the facade of the building. Also another the Europe heritage. So after final render. So what's new? So the new in my research, also in the past few years, I'm working on integrate topology optimization method with the swarm intelligence, but simultaneously. So the left side is the BSO method working on building. The right side is swarm intelligence by Roland Snooks. So I have shown both examples in the previous slides. So my research is to integrate multi-agent and also structure on the based on the structure performance principle. So from the theory to the method to the application in my PhD study. So so you can see the new algorithm I developed. The result is quite interesting. Using the different data to control the final results. So this is the best final testing using the swarm and multi-agent system to run the best structural performance of the cantilever. This is 2D. Then later on, we test on the 3D, and also test on the short 3D cantilever, but with a tracing load, which can create an intricate structure, also can create the high performance structures. So we write this, we call this new code is a Swarm BSO, and I present in the Scheduler and Sound conference. If you're interested in, you can download and have a look. And the recent work I'm working on is integrate with the CFD and the topology optimization. So CFD is computational fluid dynamic tool, then plus with topology optimization method, and working on the Taihu stone and the Marie coral, which is artificial one, and working with the students to testing and analysis the CFD results and apply the BSO algorithm on it. And which is can creating the porous space. Yeah, so we are still working on this and want to develop this algorithm into the Grasshopper plugin. And also last year we invite Professor Philip Yuan is a visiting professor for the design studio at MIT called Intelligent Force Printing. So this is the final video of the results. Yeah, so this is 3D concrete printing, and from last year, and this year I lead another project with Dr. Dan Lo from the University of Queensland in Australia, so which is called weaving technique. Yeah, there's also a collaboration project between MIT Architecture and the University of Queensland, using the topology optimization method to design the shell. So you can see at the background, and also using the carbon fiber welding technique to fabricate this pyramid. So that one, yeah, just finished last month. So I think this is the last project I want to introduce in this presentation. And yeah, we are also going to publish a paper to introduce the more detail of the project. So yeah, all the project collaborate with different peoples. I want to appreciate. If you have any question, you can email to my MIT email, also as my website. The FormX Tech will launch soon next week. And if you are interested in the work we're doing, you can follow our Instagram. So that's all. Thank you.
Okay. Thank you, Nick. I think my voice is kind of duplicating. Are you able to hear me, Aditya, clearly?
Yeah, it's all good.
Okay. Okay. So I think thank you so much, Nick. I mean, it was a wonderful presentation. It's always good to see your presentation because every time you present, there is something new which you bring as questions for me myself. Because I've been closely following up on the progress that has been made in the last 3 years. I think from 2019 to your work now. What is interesting, I think, for me is to see those 3D printed, FDM technique models to reaching to a stage which is so lightweight as the weaving tectonics project that you are doing. So it's quite interesting how your workflow is still kind of questioning the methods of fabrication. So you've been always looking at the topological optimization to working towards having a more robust system for the robots, for the 3D printers, for working on site, connecting pieces on site. So it's quite interesting, which also leads me to a lot of questions for you. But I do want to give a chance to our audience who's been here, who's been listening, spending their Friday afternoons with us. So I think I'll just lead with Rushali. Do you want to ask your question first, and then maybe we can mix it up and ask some more questions?
Yeah, I saw the
Yeah.
one question.
Yeah,
Charlie,
okay, I'll read it out. I'll read out her question. So Rushali is connecting from Mumbai. Her question is that these forms have been explored based on its materiality. So how could this be explored with stone materials like marbles or granite? Its manufacturing and fabrication process. So
yeah. So when we're doing the topology optimization, we always input the material properties. If you can find out the stone material properties, you can also you can also import into the algorithm. So when so if you start using the Amoeba, you can know there's a you can import different material. You can import the steel material, plastic material, concrete material, and if you want to use some customer material, you need to find out the material property and the density of the material. So you can import this data into the algorithm. Then it can help with the your very specific material. Yeah, I think it can. I think my answer is useful.
yeah, I'm sure. If Rushali or anyone has any other questions following up on that, please drop it in the chat. We're still discussing, we're still having some more questions. Aditya, do you want to take up some questions or should I begin? Okay, I could not hear you, but yeah, I got it that you want me to start. Okay, so I think Nick, my first question is amongst the first few projects that you showed on from Venice Biennale and some of the other 3D printed projects, where also you are doing. Yeah, Hello. Yeah.
Hello.
Where you're also looking at a certain method of form works which you're using to cast into the materials. So my question is that in the process of doing these agent body simulation, how do you even consider your digital fabrication process to become more and more modular? Because I understand that the forms are quite complex and they are special at each and every junction of your fabrication process. So could you elaborate on how did you manage to finally kind of make it more modular, or if you're considering to do so? Yeah.
Yep, that's a good question. So maybe I can go back to the one slide. Can give you very clear answer.
Yeah. Yeah.
So you can see this image, right?
Right. Right.
Um,
Right, right.
okay. So for example, this project, you can see this one have four similar agent bodies, which is similar modules. But when we want to do this project, it looks quite different in each module, but actually they have a very similar parts. So back to this, the blue one is always the same. Only different is the leg size. So it gives you a sense they are all looks different. So the modular part is in the middle. So the leg can be longer, can twist this way, can twist this way, but we're always keeping the major part is the main module things. So it can helping with the mass customization fabrication.
Right. Okay. I think following up on that, another question which kind of comes up to my mind is related to the, yeah, sorry, you can hear me clearly? Yeah, okay. So I think following up on that, another question which comes to my mind is the tool parts that you consider for the machine. Because for now, what we saw in most of the projects where you are doing 3D printed parts is that we are following a contour or a process of FDM deposition. So how do you take the
Sorry,
consideration that sorry, yeah, you can't hear me, Aditya? Am I audible? Yeah. Okay. So
Yeah, you're audible.
uh, I think Nick has a problem with my. Nick, let me know when you're ready and I could ask the question.
yeah, sorry, I lost my audio. So can you repeat
Ah,
your
okay.
question? Sorry
Yeah.
about that.
So now can you hear us? Is it all good? Okay. So I think, yeah, I'll just reiterate my question is that if we are looking at the FDM printing method from your topologically optimized models, how is it that you're considering the tool parts of the machines that you're using? Because you're clearly using some robotic arms, you're clearly using some 3D printed methods with even using metal and using fuse deposition methods. So how do you think, and how do you start to look at contour crafting to even optimize the workflow of your time that is taken in digital fabrication, or even properties of the body that you're of the form that you're making? I see that in the last project you are also looking at the one done with Philippe, is that you're also looking at non-planar printing. So at that point, a non-planar method also comes into picture. So could you elaborate on what's your thought on that?
Yes, so be- the reason we use the robotic fabrication because we always design the intricate form. So the robotic fabrication can achieve before a CNC cut and also the bending, but this also making we want to explore the more advanced and innovative way. So we're using the 3D printing. Also, the 3D printing can help us to reduce the material waste. Also, we don't need to have form work and more accurate. Like the few project I done for the X form, yeah, we only use one robot and spend 200 hours, but reduce the labor. And yeah, so that's the benefits when we're using the robotics on the fabrications. Also, when we are designing some project, we're also doing some using some algorithm to reduce the draft angles, which can help robotic printing it achieve very difficult area. So yeah, I think yeah,
Yeah.
my answer was.
Yeah. Okay. I think we also have a question from audience. Any life scale architectural applications other than installations or prototypes? So do you want to maybe elaborate on the scale at which you have been working in different projects?
Yes, yeah, good question. Before back to the university and also start this research, I'm an architect and I'm practicing architect for many years, and I have a license. But you know, most of architecture in the world, except Zaha Hadid and Frank Gehry, they did very amazing projects. But for my area, we haven't achieved the large scale and the life scale architecture application, but later we were working on it. So the final project, the second last project I'm showing you for the with the Philip is already becoming the large scale, one-to-one scale. And also we got several projects gonna doing in China as a 3D printing house design and architecture, yeah, big scale, one-to-one scale architecture application. So it takes time.
Good. Richa, you have any questions?
Yeah, hi Nick and hi Aditya and Bhavlin. So I have a question like more towards the technological, like software side. You said you have used BESO simulations and SWARM, which I'm not pretty much aware of. So someone like me, how can we direct ourselves towards some of the forms that we're exploring? So certainly you have some sort of form that you are showing to us, but there might be the other ones which are maybe more pointed, or how they are driven and how do you use software at your ease to make them possible.
I mean, how to use the BSO
No,
algorithm?
like for example, there's certain type of form that like just behind your background I can see certain form.
Yeah.
That's one type of a form. Then there can be a different linguistic to the any element. So you take inspiration from something and then you carve it out. Now those inspirations, if you can talk about, and how do you translate that using the software to build that 3D? So that process can be helpful for us.
Yeah, good question. Because the BSO method is take the false, take the false as a factor to build something. So we always like nature false, like wind false, also some animal they are hanging on the wall, and like an apple which are hanging on the ceiling or hanging on the tree. We're taking the nature force and apply on the BSO, then to create some biomimic ideas. So all this, how we gonna apply the force is depending where we get inspiration from. Yeah. So
So can
I
these
mean, the nature can give you idea how you're gonna apply force. Then you apply the force on the BSO amoeba algorithm to achieve the geometry.
okay, and can these forces be very contextual, like site specific?
Yeah, you need to do some analysis and to testing what kind of force. Yeah. Do you remember some SOM, they designed some facades which in Hong Kong. So apply the force on the two sides. So on the top side is very big wing load, then lower, smaller. So they create very intricate SOM facade. Maybe you can search on Google. Yeah, there's a lot of things from nature. Yeah.
Okay. And like, I don't know, if in BESO, can you calculate the energy simulations, like maybe how much carbon and how much energy this
But
space you can take? No.
yeah,
So you
it's
have
just
to
the
do analysis.
optimization and the form finding software. It's not analysis, but you can analysis this
No,
careful.
no.
Not
So my point is, like, if you can give the parameter of some energy calculations, and then it can find the form for you.
currently it doesn't have this function, but I will suggest them to developer. Take your advice.
Okay.
Yeah, you can. I think you can always use some other plugins to your form and reiterate and go back and forth between the process till you achieve that optimization result. But topological optimization is very interesting to kind of touch upon as a topic when it comes to a lot of other concerns of material and the footprint uh, and even the energy simulation and even fabrication methods. But I think, yeah, but Nick, that also brings a very interesting kind of thought for me to discuss and elaborate is in this process of iterations, right? Because you're topologically optimizing and you are constantly coming up with iterations. Where is it
Yep.
that you stop in the process? And does that process also affect the workflow that you have to make for your digital fabrication? So how does that happen in your office, in your studios? Where do you actually stop optimizing? So
Yeah, that's interesting. My practice is doing the architecture, and so I'm a designer and also working on some projects. So the reason I set up the FormX tech is to helping to develop the new tools for the 3D printing to realize my design, to realize some intricate design like what Roland Lux did and Philip Yuan did. So this is my the reason I set up the form for. Yeah. And also some small practice or small exercise we can ask students to testing, because students are also very interested in this kind of design and fabrication method. So, but in the university we cannot build very large scale building. So that's why they always more are working on a small prototype. Yeah.
right.
Using the new material, using the new algorithm, and using the new technology method to test. Yeah. So what I mean the new material, because we are not scientists. So the new material is like what I show in the carbon fiber things. So external is the 3D printing plastic. Internal is the resin, then the structure, which is the new material can be new composite. Doesn't need to be the new different
Right.
material. Like we cannot create a new concrete, but
Right.
we can mix the concrete with the steel. We can mix the concrete with carbon fiber. So this our exploration and also application. Yeah.
Yeah, I think interesting question by Richa. Do you have any summer schools coming up, or how does anyone apply to RMIT for their masters?
Yeah.
Yeah.
So I'm always running some workshops in Digital Future Casualers. If you check my Instagram, I just finished one casual workshop. Um, and yeah, so summer school, we don't have summer school at MIT. It's only for the MIT student, but you can join Digital Future. I mean, in June or July, then we will lead you to spend 7 days for like form finding amoeba use. If it's possible, but it's impossible right now, we can travel to China, build up the pavilion like what we did in past years. For MIT, yeah, you are very welcome to MIT School of Architecture. and urban design. We have very good teachers like Alisa and Roland Snooks. So yeah, we're running different studios. Yeah, welcome to apply. There's quite a lot Indian students at MIT, and now they're pretty, I mean, like parametric design, and some of them already graduate and find some parametric computational designers job at the Melbourne. That's quite good. Yeah. So the metal print project also, the assemble team also have two Indian students. They are already graduate, but they're still coming back to help us to assemble.
Okay. Nick, there's one more question in the chat. Do you want to take it? If one takes its application on structural elements, such as I think beams, columns, then what are its benefits over traditional based approach for these elements? I think, Nick, you touched upon this topic, but if you want to summarize and conclude on what the question is.
Yeah. Yeah. So the traditional way, the way we are doing like tree-like branch is one is showing how this algorithm can achieve. But for some engineers, because the topology optimization is start from engineer. So some engineer using this to do some bit boring structures. They just making a column, then dig some holes, which is for the real traditional way to do the design. But we want to make it more interesting. But the major idea is to reduce the material. If you can, the one column, if you can reduce the material like 20% of material, then you can still achieve the same performance. So it will help the industry, help the construction save a lot of money. And also later we use a robotic fabrication directly to 3D printing the geometries. It also save a lot of money on the mold making. So that's the reason we want to change the traditional way, both on the design and both on the fabrication, which can help with the using the design to change the fabrication, to use the robotic to change the fabrication, to save the money for the clients, also for the government as well. Yeah. So I hope this one also including the last questions. Yeah, for this lecture.
Yes. I think, yes, this brings us to the end of the session. Aditya, you have anything to say? Anything to say? Add? We can't hear you. Yeah. Aditya has been here setting up and doing all the back-end process with you, Nick. He's been reaching out and helping out with all the sessions, and also whenever you guys are looking at any of our previous session, which also includes a session with Vishu Bhushan, which happened in the month of early month of Feb in 2022. You can write to us, and these sessions are available for you to watch at any point. Some of our upcoming workshops are also very interesting. If you guys are interested, please follow the Instagram handle Nudes in the Classroom. And we look forward to a very exciting year, Nick, both for you as well as our further collaborations on Nudes in the Classroom. So thank you so much. Thank you so much. Yeah.
Thank you for listening.
Thank you, Nick.
Yeah.
Bye.
Bye. Bye, Nick. Aditya, maybe we can stay back and
Yeah.
we can record the